Okay, so all I want to do right now is just continue through this book. We're doing the book one, the prerequisites of digital physics, and I'm just showing the real basic stuff. I'm going to skip over most of the stuff, but basically what we're going to try to do is figure out what the root process of the theory of everything is. You know, how would the theory of everything actually be coded from the inside out? I'm going to show you that right now. Okay, so this is in the same little book. It's all free. Just look at it if you want to. We will now program the theory of everything from scratch, and we're going to learn Visual Basic while doing so. What I skipped over was the idea of non-stop computability. You know, if it's going to be a universe, then the program shouldn't stop, like from programmatic errors and stuff like that. And so I just made that statement. Okay, is that you know, when they look at physics, they got some ideas about, you know, the law of momentum and stuff like that. And then the idea of making it an informational universe, well, they just take the laws of physics and all the stuff that they already know, the Newtonian physics, and they try to retrofit that back into programmatic code. Okay. But I don't think it works like that. I think if it's an informational universe, you have to start from the inside out. Like that's what I'm trying to explain here, okay? So I'm going to try to start from the inside out with these most basic manipulation of numbers that I'm possibly there could possibly be to make virtual reality like I showed you above, right? So anyway, the idea is that the most important thing in this design, we're not starting out with the laws of momentum and the photon emission stuff like that. The idea of this is first, this is a program, okay? So the first thing that's most important about this program is it has to run. The most important aspect of the design of the TOE, as far as I'm concerned, is that it has to run without stopping. If it doesn't run, there won't be a universe, okay? So the first thing that this program has to worry about is the program itself not stopping or not going into some infinite loop or going astray, you know? It has to keep everything in order. So I'm calling that non-stop computability. And I'm saying that the design of this TOE, the most important thing is not, you know, making a universe that's got little frogs in it or anything like that. The most important thing in my design here is to make sure it doesn't stop no matter what. That's the first. If you're a program, the most important thing is to make sure the program runs. What the program actually does, that's secondary. If the program ain't running, it ain't gonna do nothing, right? So the most important thing is non-stop computability, right? All right. Man, I should have just shown you the sections. It would have went quicker than the way I'm explaining it right now. Okay, but anyway, here we go, okay? At a minimum, the algorithm is repeatedly manipulating a list of numbers, which emerges into our reality as matter moving through the passage of time, like I just showed you above, right? Okay, so that's what we have to do, right? We have to do that. And we also have to do that non-stop. There can't be any errors or infinite loops or anything like that, right? Okay. So here, let's keep going now. Okay, that's a good start for our TOE. Okay. Now, to just build on the example that we already gave, I know the algorithm number one that I gave you, that's not the TOE, obviously, right? But we're going to build upon that, and I'm going to show you how we're going to actually turn that into the TOE, okay? So here we go. Algorithm number one, rendition A, is, okay, here it is. Hope you can see this. It says, while true, call TOE and while. That's the whole program, is those three lines right there. The stuff in green is all comments. So that doesn't affect the program, it just makes it easier to read, okay? So what we're doing here, this is Visual Basic, While true, that means that means repeat the algorithm for the age of the universe. So how long is that? That's forever, baby. Okay. I know it's only supposed to be 4.7 billion or 14.7 billion years old or something like that, but uh, um, the way it actually is going to be executing is just going to keep running forever. Because for all we know, the universe may like expand off and then come back to the state that it was at in the Big Bang and then go again. If it did that, that would be infinite time. It would just keep repeating the little cycles. Okay. So I'm saying that it runs forever. The age of the universe is forever. Okay. How long has this algorithm been here? You know, it's naturally occurring, and nobody ever had to write it. It's just like 2 + 2 = 4. How long has that existed for? That has existed forever before man. By the way. Okay. Anyway, I'm getting a little off the track here, but anyway, so that's the whole TOE right there. We're just going to keep applying that algorithm again and again and again. Like I was going to go state 1, state 2, state 3, keep going, okay? And I hope this is simple enough. I realize it looks really simple. So simple, it's so stupid, maybe you don't want to look at it, but just trust me, it's going to get a lot more complicated. I just want to make it really clear what I'm doing for people that maybe are not programmers. And I say, note this is actual VB code, and there's all code examples are available for download. You just click this link here; it'll show you a directory of all the versions that I've got. You download algorithm 1 and 2, and all the things that I actually show you in this document. You can actually download them, and you can actually run them and try them yourself on your own computer. So continue on, I say the universe must run forever. And that means the algorithm must exhibit what I'm calling non-stop computability. And then I go on and explain this. I don't want to get too detailed here, but what I do, I just keep adding more and more stuff to this algorithm, okay? First thing we're going to do, we're going to add something called a tick counter, okay? And the tick counter here is just a little counter. It counts how many times we're going to call this routine here, okay? All right, so that becomes rendition B. All right. So now I go ahead and demo the actual example I gave up above, the one that we said, this one here. But I'm going to demo this now in actual VB code that you can actually run. And we do that right here in rendition C. We have a tick counter. We have something called a particle list right here. And the particle list, that becomes our list of integers right there, right? And this is how you do it in Visual Basic. And then we go ahead and then we add 1 to it and all this stuff. And here's how, so this right here, this rendition here is actually implementing that example I gave you there all in Visual Basic. And if you follow this from step to step, you're going to pick up Visual Basic itself. It's that simple. That's why I chose Visual Basic. It's the most English-like language there is. Most English-like programming language. Very, very simple. Then we talk about non-computable algorithms, and what I'm saying here, if I just execute this program the way it's written right here, it'll run fine, but then it'll blow up, you know? Because what's happened is we kept adding 1 to the tick counter, and there was nothing to stop it from adding 1, so it's just going to go up to, theoretically it'll go to infinity, but computers, they don't let that happen. You're going to have an integer overflow, and it's going to crash, okay? So the point I'm trying to make in all this jargon here is that, yeah, you have to have limits, you know? You have to have checks. You can't let it just go to infinity like that. So you have to have constructs. For example, I've got a construct here. I call it a digital overflow, where you can count the thing up to a certain level, a tick counter, and when you hit that level, then you reset it back to 0. Okay, kind of like that. That would let the universe keep going after the tick counter had run out. Because the thing is, you have to have finite limits to all these numbers that you're calculating here. Theoretically, you could use infinity. You could use that number line off to infinity, but in reality, you can't do that. You can't compute infinity, okay? Because if you try to compute infinity, It would take an infinite amount of time to compute infinity, and you would never return from that subroutine call. You know, this one here. You know, if you call TOE, if it has to do something inside of here that's going to take infinity to take, then you're never going to return from that call. You're never going to continue the universe. Okay, so everything has to have finite limits. Finite limits. So it's a part of a foundational key to constructing the TOE. And right away you can see that would not allow something like a time-space continuum to ever be computed. A time-space continuum would require infinite resolution, and you would never be able to get out of this subroutine call any time. You know, you call TOE, it would try to go do something through space, but since there's infinite resolution, it would never ever be able to complete that, and it would never return from that call, and time would cease. You know, so there can't be infinite space, infinite resolution. It can't. The universe can't be infinite, and also can't be subdivided infinitely as well. It's got to be in whole chunks, and it has to be a finite number of chunks. That's the way the universe has to be processed. Otherwise, it can't be processed. And again, I'm approaching this from a processing standpoint, not from a physics point of view that's trying to retrofit back into code. Okay, I'm saying these are fundamental aspects of coding itself, and that's what should decide how the TOE is written. I hope you're following me.